Section 25. Okay, I will broadcast in just a moment. Pigeonhole Principle is the name of this section. It is a way of proving things by basically thinking of it in terms of you got a coop, like a pigeon coop or chicken coop, and you only have so many holes, so many places for your pigeons to go. If you have N holes, let's say we have P pigeons and H holes. Well, I'll tell you what, even before I talk about the pigeon coop, let me just ask you a question that's kind of in the vein as the rest of the questions you're going to be answering in this section. The question is this: how large of a group, can't spell today, sorry, group of people must you have to guarantee that at least 2 people share a birthday? That's month and day, not year. Okay, this is not the traditional birthday problem of what are the odds. You know, how many do you have to have? There's a famous probably talk about statistics of how many people you have to have before the odds of 2 people in the same room having the same birthday is 50-50. This is just how many people do you have to have together before you're absolutely certain that 2 of them have the same birthday.
367, because if you include the extra.
Yeah, I asked my wife Lori this question, and she said 366, and I had to make a face at her, and she almost slapped me, but she was wrong. It's 367. Why is it 367? It has to be more people than there are possible days, right? And it is possible that somebody has a birthday on February 29th, which is the 366th day of the year. So as soon as you get to 367, it's absolutely guaranteed that 2 have the same birthday. Okay? And the reason for that is the Pigeonhole Principle, right? So the Pigeonhole Principle, again, like I was talking about before, says you have, imagine a pigeon coop. You have P pigeons. You have H holes. Okay. What's the relationship between P and H that guarantees at least 2 of them have to share a hole? If the number of pigeons is strictly greater than the number of holes, if P is greater than H, then some pigeons will share quarters. Does that make sense? So all of the problems we're going to be talking about today is going to be the question of how many do you have to have, or if you have so many of each, of 2 different sets of objects, that you're guaranteed that at least 2 of them are the same, or in the same place, or something to that extent. I'm going to give you a few examples. Sorry, my chair just went out from under me. There's a lever down there that they put in the bad place. So I put my legs underneath me and I go to the ground. That. That's perfect. Try that again. All right. So the interesting thing about this is that you can prove things in pretty unrelated circumstances that you wouldn't expect to be able to prove things. It's actually fairly common. How many of you have ever heard of the Putnam exam that we have students participate in each year? Dr. Thornhill has spearheaded an effort to continue our participation in the Putnam exam. It's a really hard test that is administered on a specific day for 6 hours. You break for lunch, but it's about as hard of a math test that an undergraduate could ever take. And it's mainly just proofs. It's like 6 in the morning and 6 in the afternoon?
Yeah.
So like 12 questions total. Now the median score on the Putnam exam, and by the way, this is administered at most universities that have a math major program. So everything from, small private colleges like Wayland all the way up through Princeton, Harvard, Yale, U.S. Schools at undergraduate level, the median score, 50% of the people that take the test score 0 or lower, generally. 0 points.
Make it lower.
You can't get lower.
Did we have someone score?
Yeah, you can't get lower, you're right. So 0, less than or equal to 0, which by the way is still 0. I can say that mathematically, it still makes sense. But yes, 0 and not higher. Whatever. The point is it's really hard, right? So if you get a little bit of one right, they'll still give you partial credit, a point or two. We've had, I think, up to
Jeremiah
about,
got a point.
he got 1. I think Emily Willems a couple of years ago got, I think she got close to like 10, like 8 or 9, something like that. Which is the best we've ever done on it, but that's still saying something about our program here. Somebody can do that.
How many points are there?
Well, every question's worth 10, so you can get 120. And then your school's team score will also be ranked, and so you can imagine that Harvard and Yale and Princeton are all, and Caltech and MIT are all competing for that top spot. But to have a school that scores with students above the median is significant, and we have done that the last several years. Yes, sir.
Has anyone scored a perfect score?
Yes, I think that has happened before.
That has
I didn't take it. I didn't know about it until
Awesome.
after I was a faculty member. I helped get it started here. One of our adjunct faculty, in fact, over in the School of Business, Roberto Nass Worthington, he was a math major while he was here as a student and came to me one day and said, "Can we please take this test? Like, I've never heard of it, but I will figure it out and make you take it." So we did. So we started it way back when. But anyway, the reason I bring it up is that seems like every year or every few years there's a problem on there. The Pigeonhole Principle is the key to unlocking, which you wouldn't think that something as simple as how many pigeonholes do you have and how many pigeons do you have answer the question of one of these really hard questions, but it actually turns out to do that. So let me show you a couple of proofs of some examples of things that we might use the Pigeonhole Principle for. The first one, you would not expect the Pigeonhole Principle to apply, but I've got a really good example. He uses this in the book, 25.1. Let n be a natural number. Then there exists an a and a b that are natural numbers, with a not equal to b, such that n to the a minus n to the b is divisible by 10. So take any number, just so you can kind of see what this proposition is saying. Let me do an example with some numbers in here. Let's say n is, the one he uses in the book is 17. The question is, can we find a power to raise 17 to, and another power to raise 17 to, so that when we subtract them, we get something that's divisible by 10. Now, this proof is not going to tell you how to find them. It only tells you that they exist. The one he comes up with in the book is 6 and 2. Turns out that 17 to the 6th power is 24,137,569. And 17 squared is 289. I'm not telling you where I got the 6 and 2 other than just guess. In a minute, we'll prove why we know that such numbers have to exist. So if you subtract those, you get 24, 137, 380, 280. Thank you. Now, how can you tell that's divisible by 10? ends in 0. So that's going to be one of the keys here. Note, a number is divisible by 10 if it ends in 0, right? Which, by the way, then if two things are subtracted and the result is 0, what does that say about the two things? Well, no, they're not divisible by 10, but how did I get a 0 here? They have the same last number, the same units digit. Okay? That's going to be the key to the proof, is that if you have some natural number, let n be any natural number, consider the numbers and just start raising n to different powers. N to the first, n to the second, n to the third. And just keep going. And I'm going to go 11. In a minute, if it's not clear now, it'll be clear why I went 11 places. Think about the ones digit of these 11 numbers. The ones digit of each of these must be from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How many choices do you have? So the ones digit of each of these up here must be one of these 10 numbers. Right? I have 11 numbers, of which the ones digit must be one of 10. So what does the pigeonhole principle then say? Here's your pigeons. Here's your holes. Two of these numbers have the same ones digit. Guaranteed. They have to live in the same hole, right? Which implies at least two of these numbers, right? Into the A, into the B, have the same units digit, which implies that n to the A minus n to the B has to be divisible by 10. They have to have the same units digit because there's only 10 to choose from and there's 11 numbers there. That's the pigeonhole principle right here. The pigeonhole principle. So, there's really no clue in the proposition itself that that's going to be the technique. You get creative, and that's one more tool in your toolbox. You can try the pigeonhole principle to see if it works. So, proved. Boom. I'm going to do one more, and then we'll move on to the next section after that. Any questions about that proof? Does it make sense? Why it has to be true? That's the key. Not that you would come up with it on your own. To be honest with you, I don't think I would have thought of that as a technique to prove that. But once I see what my pigeons could be, which is the choice of n different numbers to a power, and then what the choices are for the unit digits, I know that I have more pigeons than holes, so they have to repeat the units digit. And if they repeat the units digit, then when you subtract them, they end in a 0. They end in a 0, then it's divisible by 10. Voila. All right. No questions? Moving on to the next one. Another one that is provable by the pigeonhole principle. Let's say we're given... Actually, I tell you what. I need to insert in here... well, I'll put it afterwards. Given 5 lattice points. So I need to know what a lattice point is, so I'll put a definition after this in just a second. in the plane, at least one of the line segments connecting the points has a midpoint that is a lattice point. All right, so we got to know, of course, before we prove this, what is a lattice point? Has anybody ever heard of a lattice point before? I had not before this class. Take a grid like 1, 2, 3, 1, 2, 3. I'll do this in maybe red here. Draw some horizontal dashed lines at each of these integers. In fact, you can do this at any integer, not just 1, 2, 3. And then vertically. So these points right here, this one, this one, this one, this one, and so on, this one, this one, this one. Those are all the lattice points. And they keep going. So, I mean, they'd go off in this direction, they go off in that direction, they go off in this direction, and go off in this direction. So based on that, what do you think makes something a lattice point?
Coordinates?
Is it coordinates integers?
If coordinates, yeah, the coordinates have to be integers. Okay? A lattice point is a point whose coordinates are integers. So, the theorem here says, or proposition says, if you take at least 5, so 5 lattice points in the plane, pick any 5 you want. Maybe this one, maybe this one, maybe this one, maybe this one, and maybe this one. There is a line segment connecting 2 of those where the midpoint of that line segment is itself a lattice point. Okay, now if I connect all of those, there's actually quite a few of them, right? This point to this point, this point to this point, this one, this one, this one. All the different ways of connecting my 5 points together. At least one of those line segments has a midpoint that is a lattice point. Notice this one right here works. Doesn't it? The midpoint of that line segment is a lattice point itself. Halfway from this point down here to this point up here. No matter which 5 you choose, we're going to prove that you're guaranteed to have one line segment that has a midpoint right in the middle that is a lattice point.
Even if you have a really big thing?
No matter how big or how small, we can use the pigeonhole principle to prove that once you get to 5, you're guaranteed one line segment that has a midpoint that's a lattice point. So how do we prove that? Proof. Okay. We have 5 lattice points. Recall the midpoint of a line segment from, let's say, AB to CD is, do you remember the formula for midpoint?
X1 plus X2
Yeah, it's the average of the coordinates, right? So a plus c in this case divided by 2, and b plus d divided by 2. Okay, so my 5 lattice points are going to be my pigeons in this case. We've got to decide what holes are we mapping them into. So here's kind of the key that unlocks this. If you can think of this, you realize the rest of it kind of falls out. When you add two things together and divide by 2, if A and C are both odd or both even, then their average is going to be an integer, right? An odd plus an odd is even. An even plus an even is even. You divide by 2, you get a whole number, an integer, I should say, right? And if B and D were both odd or both even. So let's think of our lattice points, our 5, in terms of their parity, in terms of their odd or evenness. Parity is a word to describe that, often used in this context. So there are choices for oddness and evenness, right? What are the 4 possibilities? You could have your 2 points are both odd. That is, your 2 coordinates are both odd. You could have one is odd, the other is even. You could have one is even, the other is odd, or you could have even, even. Agreed? Now there's 5 pigeons and how many holes? 4 holes. Which means at least 2 of the lattice points, the 5 lattice points, share their type. Which means no matter which one of these 4 they are, they're either even odd and even odd. They're either the same of each other, right? Which means you choose A, B, and C, D with the same type. Which means that A plus C is even. Now why is that even? Well, A and C are both odd together or even together. They have the same oddness or evenness. Since they are both odd or both even, which means A plus C over 2 is an integer. The same is true for B plus D, which means A plus C over 2 and B plus D over 2 is a lattice point because those are both then integers. Proved. Guaranteed. So the hardest part about the pigeonhole principle, well, there's 2 hard parts about the pigeonhole principle. One, in kind of in the wild in general, when you're out in the real world, when you're out in the math major world and you're not in class doing homework, but you come across a proof or a theorem that you need to prove, to know that the pigeonhole principle applies is hard. Okay? You have to think through what could be the pigeons and what could be the holes. Okay? And so that's the second hard part. That's the challenge in today's homework assignment for this section is, in every problem that I give you, you've got to identify what are the pigeons and what are the holes, and can you show that there are more pigeons than there are holes. Okay? So in all the homework problems that I've given you, that's the key. Okay? And that's the end of that section. So I'm going to stop the video there and we'll move on.